This is Lesson 5 in our Calculus 3 series, Lines in Three-Dimensional Space. In two-dimensional space, we know that a line is specified by a point it goes through and its slope. And sometimes we're given 2 points and we find the slope between the 2 points. Similarly, in three-dimensional space, a line is specified by a point it goes through and its direction, but now its direction is given by a vector. And we can also find the equations of the line by using 2 points on the line and finding the vector between them. Given point P0 on the line, here's P0, and direction vector V, so this line is following the same direction as V. For any point P on the line, we have that P0P, the vector P0P, must be parallel to vector V. P0P is the vector determined by those 2 points, and V is the direction vector for the line. So again, looking at the image, we see that P0P is parallel to vector V, and this is for any point on the line. Remember, parallel vectors are scalar multiples of each other. So even if we have a point P back here and the vector is going in the opposite direction, that's still okay because it's still going to be a scalar multiple of vector V. Now let's see what that means in terms of equations. If P0P is parallel to vector V, then P0P is equal to some scalar times vector V. So we're going to call that scalar t, and we've got P0P is equal to TV. And in component notation, what does that look like? P0P is x minus x0, y minus y0, z minus z0. And vector v in component notation, we're calling a, b, c. So TV is going to be TA, TB, TC, or we can write it as AT, BT, CT. So equating the components of these vectors, we have x minus x0 is equal to AT, and y minus y0 is equal to BT, and z minus z0 is equal to CT. So we're here with those equations. And then now just solving for x, y, and z, we're here. We have x equals x0 plus AT, y equals y0 plus BT, z equals z0 plus CT. And these are the parametric equations for the line through x0, y0, z0 in direction ABC. Now let's take a look at the situation in vector form. So we've got the same picture here, but instead of just talking about points P0 and P, we're going to talk about position vectors for those 2 points. In other words, vectors that go from the origin to those points. So we've got vector R0 going from the origin to P0, and vector R going from the origin to point P. So the component notation for vector R0 is going to be x0, y0, z0, and the component notation for vector R is going to be x, y, z. Then looking at the vector triangle we have here, we can see that R is equal to R0 plus P0P. And we know, again, that P0P is a scalar multiple of vector V. So P0P can be replaced by TV, scalar multiple of vector V. And so now we have this vector equation of the same line. R is equal to R0 plus TV. Now let's take a look at an example. We want to find parametric equations and vector equation for the line through 1, negative 2, 5, parallel to, or we can also say in the direction of 3, negative 1, 2. So we're going to start with our parametric equations of the line. When a question says find parametric equations, the first thing you want to do is write down those parametric equations and then look at it and see what needs to be filled in. You can see the x0, y0, z0 needs to be filled in, and the a, b, c needs to be filled in. And that's exactly the information we were given. We were given x0, y0, z0, and we were given a, b, c. And so we just go and plug those in, and here are our parametric equations for this line. Now for the vector equation, we need a position vector. Instead of the point 1, negative 2, 5, we're going to be talking about the position vector R0 with components 1, negative 2, 5. And the direction vector stays the same. And so our vector equation again is r equals r naught plus tv. So we can write this in basis vector notation. R naught would be I minus 2j plus 5k. And the direction vector v would be 3i minus j plus 2k. We have a tv, so the t gets multiplied there. And then we could, if we want, combine so that we have 1 plus 3ti minus a 2 plus tj and plus a 5 plus 2tk. And notice the coefficients that we have here for the basis vectors are exactly the same as the equations we had here. Now going back to the parametric equations we found the parametric equations for this line, x equal 1 plus 3t, y equal negative 2 minus t, and z equal 5 plus 2t by using the direction vector 3, negative 1, 2. And we can read that right off of our equations here, 3, negative 1, 2. Those are the coefficients of t in the parametric equations. But consider the vector 2v. 2v is 6, negative 2, 4. They're in the same direction. So we should be able to use 6, negative 2, 4 in our parametric equations and get the same line. And in fact, these parametric equations and these parametric equations represent the same line. It's a different parametrization, but it's the same line. It's the same set of points in three-dimensional space. The difference in the parametrization is that we will be at different points on the line with different t values. For example, with t equals 0 in both of these lines, we're at 1, negative 2, 5. We're at the point 1, negative 2, 5. But if we want to get to the point 7, negative 4, 9, we would need a t equals 2 in this first set of equations, but just a t equals 1 in the second set of equations. So we would say that the first parametrization moves a little bit slower because you need a higher t value to achieve the same point. But in any case, both parametrizations represent the same line in three-dimensional space. Now let's take a look at this example. Find the parametric equations of the line through the points P and Q. P is 2, 1, 3 and Q is 4, 0, 2. So again, first thing I want to do is write down my parametric equations of the line. And what needs to be filled in here? We need an x naught, y naught, z naught. That's a point that the line goes through. Well, we definitely have that information. Actually, we could choose from either of these. And we also need a direction vector for this line. And that we're going to have to create. We're going to have to use either vector PQ or vector QP. If we use vector PQ, we're looking at 2, negative 1, negative 1. If we use vector QP, we've got negative 2, 1, 1. So actually these parametrizations will be at the same speed but in different directions because the factor between the two is just a negative 1. So now we have some options here when we're setting up our parametric equations. We said that we need a point x naught, y naught, z naught. Well, you could either use point P or point Q. We also said that we have two different direction vectors that we're looking at. One is the negative of the other. So we could use either of those. So I've got 4 solutions here. Just to be complete, I put all 4 of them here. And they all represent the same line. They're different parametrizations of the same line. With this parametrization, we used for these equations point P and vector PQ. So that means when t is equal to 0, we're at point P, and then we're going in direction of vector PQ as time moves positive. If we start at point P and use vector QP, then again when time is equal to 0, we're starting at point P, but we're moving in the opposite direction as time goes forward, as time is positive. Similarly, we can start at point Q, go in direction of vector PQ, or start at point Q and go in direction QP. All 4 of these represent the same line with just different parametrizations. Now let's take a look at this sketch. I'm starting with point P, that's 2, 1, 3, so I'm going out 2, over 1, up 3, that's this red point, and I'm using this parametrization in direction of vector QP. So I'm going from this point, I'm going back 2 units, over 1 to the right, and up 1, right? I'm using vector QP. So that takes us here. And I've also sketched in the rest of the line as well, but I want to talk a little bit about the parametrization. At t equals 1, with this parametrization, we're at the point 0, 2, 4. 0 in the x, 2 in the y, 4 units up. That's this point right here at t equals 1. Now, even though this parametrization gives the same line, the same set of points, what point would we be at when t equals 1 here? When t equals 1 here, we'd be at x equals 4, y equals 0, z equals 2. X equals 4, y equals 0, z equals 2. We'd be here. We would be the same distance from point P, but in the opposite direction. So as t gets greater with this parametrization, we're moving off in this direction. Using the opposite vector, we would be heading off in the other direction. Now let's talk about parallel, intersecting, and skew lines. Lines are called parallel if they have the same direction, that is, if their direction vectors are parallel. So for example, these two lines here, our direction vector for this line is 3, 2, -1, and our direction vector here is -9, -6, 3. We can see that they are scalar multiples of one another, and so these two lines are parallel. Now, in two-dimensional space, we know that if lines aren't parallel, they intersect. But that's not so in three-dimensional space. And here's an example. Our blue line here is x equals t, y equals 0, z equals 1. So we're moving in the x direction. That's the only change that we're getting. Y is staying stationary at 0 and z is staying stationary at 1. So we've got this line that's just coming forward and back in the x direction, and its height is at 1, z equals 1. Then we have this pink line that's moving off in the other direction. It's going in the y direction only. Its equations are x equals 0, y equals t, z equals 2. Notice it's 2 units high here. And these lines are not parallel, but they also don't intersect. This line's always going to be at z equals 1. This line's always going to be at z equals 2. They're never going to intersect. So these are what we call skew lines. They're non-intersecting and non-parallel. Now let's take a look at an example. Are these lines parallel, intersecting, or skew? First thing we're going to look at are the direction vectors to see if the lines are parallel. What's the direction vector for line 1? We have a 1, a 0, and a 2 as our coefficients of t. And for line 2, we have a 2, and a 4. These are not parallel. Now notice I'm using an S here for my parameter instead of T. You'll see in a minute why we want to use different letters for those. So now that we know that the lines are not parallel, let's see if they're intersecting. What would it mean if the lines were intersecting? It would mean that there's some T value here and some S value here that give us the same X, Y, Z coordinates. So we're looking for a pair of TS that work together to give us the same point x, y, z. So that would mean that 4 plus t would have to equal 2 plus 2s. And 2 would have to equal 2s. And 3 plus 2t would have to equal -1 plus 4s. So we're starting with these equations. And the best place to start would be with the middle one, 2 equals 2s. That tells us s would have to be 1. Now let's go back to the first equation. If s is equal to 1, that means 4 plus t is equal to 4, so t must be 0. Okay, so we have an s and a t that work for the first two equations. What we have to check is whether or not this s and t pair will make the third equation true. Is it true that 3 plus 0 is equal to -1 plus 4? And yes, that is true. So in fact, there is an S and T pair that gives the same point on both of these lines, and so these lines do intersect. When t is equal to 0 for line 1 and s is equal to 1 for line 2, these lines are at point 4, 2, 3. Right? When t is equal to 0 for line 1, we're at 4, 2, 3. And when s is equal to 1 for line 2, again, we're at 4, 2, 3. So these lines intersect at that point. Let's take a look at a sketch of those lines. They intersect at the point 4, 2, 3, so we're coming out 4, over 2, up 3, so that's that red point here. Line 1 has direction vector 1, 0, 2. So coming out 1 unit and going up 2, so that's that blue line, the blue vector, and then the blue line. And line 2 has direction vector 2, 2, 4. So coming out 2, over 2, up 4. So that's that green vector and then the green line. And now since we have intersecting lines, we can talk about the angle between them. So the angle between intersecting lines is the angle between their direction vectors. So we're at this point 4, 2, 3, and we've got direction vectors for line 1 and for line 2. Let's call them A and B. We know how to find the angle between those two vectors. That was in a previous lesson, right? A dot B is equal to length of A, length of B, cosine theta. So let's make our computations. A dot B is 10. Length of A is radical 5. Length of B, 2 radical 6. So we get cosine theta is equal to 10 over 2 radical 30. Theta is approximately 0.42 radians, or approximately 24 degrees. So that tells us that this angle theta is approximately 24 degrees. Now let's talk about eliminating the parameter from our parametric equations. They won't be parametric anymore, right? So if we're starting with x equals x naught plus at and we want to get rid of our parameter t, we first have to solve for it. So t is equal to x minus x naught over a. Similarly, for the y equation, t is equal to y minus y naught over b, and for z, t equals z minus z naught over c. Now since I'm dividing by a, b, and c here, I'm talking about when we have a, b, and c not equal to 0. And so we can set each of these equations equal to each other, and we get symmetric equations of the line through the point x naught, y naught, z naught in direction ABC. So for example, line 2 that we were just looking at, its parametric equations look like this. We can change that over to symmetric equations by doing x minus 2 divided by 2, y minus 0 divided by 2, z plus 1 divided by 4. So x minus 2 over 2 equals y over 2 is equal to z plus 1 over 4. And those are the symmetric equations for the same line, just another way to represent it. Now if a, b, or c is equal to 0, we can still eliminate the parameter. For example, line 1 above was x equals 4 plus t, y equals 2, z equals 3 plus 2t. We notice that our b value in this direction vector is 0. So to eliminate the parameter, we just leave y equals 2 and put a comma. And then we're going to eliminate the parameter in the other two equations. So we have x minus 4 over 1, or just x minus 4, and then z minus 3 over 2. So x minus 4 is equal to z minus 3 over 2, and y is equal to 2. And with this, we'll conclude our lesson on lines in three-dimensional space.